Right. A little loud there. Let's see if we can get back a bit. All right. Let's see. Testing, testing, testing. See if we can do this without it burning your eardrums out. Hi. My name is HdMoore, CSO for Alpha7, founder of the Metasploit projects. Been doing that for almost 10 years now. It's a lot of fun. I'll keep doing it. Cool shirts. This talk's a little different from what I planned it to be. Dave was nice enough to make me the keynote last year and then suggested I do that again this year. So I then scrambled till 4 a.m. trying to make my deck more keynote worthy. So it may come off a little bit less technical in the beginning, but I promise it gets down to nitty gritty details pretty fast. So the title of the talk is the Wild West. It's really looking at different frontiers, different things that we go kind of the great unknown where the rules don't really apply still actually applies to the internet in a lot of ways. This talk really kind of dives into all the weird nooks and crannies and funky little ghost towns and just bizarre stuff you find on the internet when you start doing large scale mapping. But the key word is really mapping and finding really neat things out there. When I was a kid growing up, I spent a whole lot of time in a camper truck, a Datsun 50 with a little shell on the back, going from Florida to California and I-10, back and forth, back and forth, back and forth. So you spent a lot of time driving around the middle of nowhere. You'd find these strange little roads that go up, up a mountain or a weird path or a little horse trail going someplace, and you really have no idea where that stuff is. And it all is fascinating to me, seeing kind of all these different directions you can go and having none of the time, resources, or even any other way to really go follow up and figure out what's up there. We found some bizarre stuff. One time we broke down next to a railroad track out in the middle of Arizona. We pulled out, we looked at the railroads, and the entire railroad, the gravel, the dirt that's usually with the rail ties, was all volcanic glass. Like these awesome clear pieces of like rainbow obsidian, like really cool stuff out there. So we just put it all in a box and sold it for a couple grand. It was great. So once in a while you find some really crazy stuff just sitting out there in the weirdest places, the weirdest holes in the wall of the world, the U.S., the highway system. You would find other stuff like climbing the mountain just for fun, like taking a break, going for hikes someplace, and you find some cabin that's been furnished for the last 20 years and no one's ever been in it. Just really odd things. You find the remnants of where folks who robbed a bank camped out for a week and beer cans littered in a circle in the middle of the woods. So you just find some really cool stuff out there if you know where to look. So I really like, just kind of getting off the beaten path once in a while, seeing what's out there, getting a feel for really, what else is going on. And this is extended to not just, driving around. I like driving down weird little roads for fun these days, but also like going into tunnels. I had a problem as a kid of getting into tunnels and often getting stuck or lost. Because they're fun to crawl through, but you never really know how small they get or where they end up till you get there. So I remember crawling through tunnels for probably 2 or 3 hours one time and popping out at the underneath an overpass, but with a grate I couldn't get out of. I had to turn around and crawl all the way back again. Another night I spent 6 hours going through a 2-foot tunnel just to see where it ended up when I was 15. And it's one of those things where it's probably the dumbest thing I could have ever done in my life, but still a lot of fun, and it's one of those kind of attractions to, where does this tunnel go? How does it connect to other things? Where does it, So, plus I wanted to find the Ninja Turtles, but beyond that, it was a lot of fun just go dig around. So it's always fun, just kind of like, no matter what you're doing, no matter what your life is like, or where you're traveling, or what you're seeing, or what kind of application you're playing with, just trying to take a wrong turn and see where you end up. This is a photo that some folks at DerbyCon may recognize. Very few people, because we had to run really fast once we found it. This is the basement of a building around here, and this is a really old school, like steampunk brass elevator that we really wanted to pull the handle on, but didn't. It took a lot of gumption not to. So a lot of fun stuff. You'd find just the most bizarre stuff out there if you start looking for it. This whole kind of, following the unknown, digging into places you really shouldn't, it's all been an obsession of mine. It kind of goes with hacker culture. You really want to just, dive into stuff you shouldn't get access to, or that you feel like everyone else is kind of ignored and you feel like needs more visibility, or, it would be fun to look at. And this has kind of driven me crazy for the last 20 years and what I spend most of my time on. I got involved doing security tools because security tools really are the only kind of software that does large-scale discovery. Scientists have things like, observatories and telescopes and fun things like that. Network nerds have ping scanners and port scanners and security tools, and that's really where you get all your new data and all your new raw stuff. Fortunately, that's gotten much cheaper to do. Now that you've got these huge racks of servers you can rent out for pennies on the dollar. If you use, spot instances of Amazon, you're paying 0.002 cents per hour for these massive servers. It's gotten much more affordable to do large-scale network exploration and computer exploration. You can find free data sets on a free tier of a free cloud provider that let you go through and do large-scale data mining of just real, random cool data. We're one of the, unprecedented times in our lives when we have abundant amounts of data and not enough attention to spend on it. So there's lots of really cool stuff out there, but you still have to go find it and codify it and classify it and manage it. The cool thing is that a lot of people are doing this stuff. You already find people doing large-scale analysis projects, data mining projects, things like that, and we're going to kind of see a lot of information technology, information security in particular, moving more towards data mining as a primary source of information going forward. It's not a matter of getting the data anymore, it's a matter of figuring out what to do with it. So this is a kind of a throwback to my talk last year. I spent a lot of time mapping phone systems. This is the screenshot from some of the Warbox prototypes I was working on. This would then dial 10,000 numbers at a time, put them into a giant grid array, and then classify them based on peak frequency of the signal of whatever picked up the phone. So if the same lady picks up the phone on 10 different lines, they'll probably have the same peak frequency in her voice when she picks it up. And the key thing about this diagram is what you'll see is this isn't random. You don't see just random pixels here. Every color here represents a different peak frequency, and it's not just the topology that's represented here, the lines and the graphs, the kind of like little pieces here. It's overall texture and kind of geology, if you will. It's the way all this stuff kind of fits together. This is a 10,000 phone number block in Austin, Texas, the downtown area, basically. And it's kind of cool seeing how all these numbers map up, how you have a lot of similarities in some areas of the block and not a lot in other areas of the block. And this is the telephone system. These are actual people's voices being analyzed to return this data. This isn't just a random network. But you do see a lot of organizations, you do see a lot of similarities, a lot of kind of textual differences between different areas of this map. So I love digging into stuff like that. I think it's really cool data, and this stuff just drives me crazy, makes me obsessive about it. But that's what I do for fun. So if you look at any kind of network, whether it's at least any kind of human network, whether it's phone systems, whether it's internet maps, whether it's internet topology, you can almost look at it like a grape vineyard, for example. For all the enophiles in the audience who drink wine and like wine, there's a thing in the French word terroir, which basically means a combination of location, soil and sky, or geography, geology, and weather. And those are the things that kind of shape it. So you can have a plot of land in one area of Bordeaux that produces wines that sell for $32,000 a bottle, right next to the same vineyard that sells their grapes that goes into $2 chuck. But it's all a matter of exactly where it is, its position relative to its neighbors, exactly the conditions that it happens to have. As you start digging into networks, and you can have the same types of devices, the same types of switches, same type of organization, and entirely different represented exposures and vulnerabilities and exposed data sets. So it's kind of neat. There's a lot of different ways you can look at most human networks and apply them to the same kind of category, where you do see some patterns emerge, but you also see some really strange textures popping out of this pattern. So this is a map we've probably all seen at one point in time. It's an internet mapping project. These folks did a topology graph, basically a trace route of the whole internet, and they went and mapped out all the different links to it. It's a pretty graph. It's freaking useless in my opinion, but it's pretty. It's got some neat colors on it. The colors are represented by the different types of networks that are on there. So green is commercial, red is military, and so on. Again, it's neat seeing a big fancy picture, but it doesn't really tell you much. It says, yeah, there's lots of stuff. So if you start looking at some other graphs, this one's connectivity between major cities in the world. So you can see density graphs of number of, basically pop connections, different peering points, things like that across the entire world, how all these connections kind of come together, the density of them. The bottom graph is the same thing, but showing the links between these different cities. So you see these, super bright lines where different major world cities are connected to each other directly. And again, it's a neat graph. It shows you some of the connectivity. It gives you a feel for who talks to who, when, and where. But again, there's not really much meat to it. Like, you can't really see much data with it. This is a slightly different graph. Instead of going based on topology, networking, or the connectivity of systems, this is based on how popular, how much traffic a particular website gets for a particular worldwide region. So the bottom left, or your right, you'll see some yellow dots that represents a lot of the Asian websites, Baidu, all the different Chinese search engines and properties that show up there. The center, of course, is all the U.S. properties, North America, more global properties these days, things like Facebook, Google, Twitter, things like that. And you see little pockets around the world. So even though we do have, a fairly good sense of what the most popular websites are, they really are diversified by region, and every region does have their own central most popular sites. So it's a good idea to look at this stuff and get a feel for what the relationships look like. If I control just one of these big nodes, how much traffic am I able to take over? How many people can I infect? If I'm going to try to deliver malware to all of my users, well, Facebook looks like a great target. So that's kind of the things you kind of look about. Those are the things you think about when you start looking at these different regions. If I'm attacking Baidu, for example, or China, to go through Baidu and so on. And finally, one more graph that I pulled off the internet. This one's a fun mapping of spam sources for particular individuals' PC. They got lots of spam. They looked at where the spam came from. That was actual UCE, and they looked at where the real email came from. And counterintuitively, he chose red to represent real email and green to represent spam. But it's a pretty cool graph. This shows you the entire block of the internet. So there's 255 possible blocks. Many of them are reserved. Like the top left corner in your view is all reserved blocks that aren't used, broadcast, multicast, things like that. You see a couple of the blocks here not being used as well. But the cool thing about this is you can actually see different neighborhoods appear. You can start seeing areas of this map that are primarily one color or another color, or the background color is primarily green, which means it's mostly spam sources, not a lot of real email. So it's kind of cool seeing how all this stuff maps out. And again, this is just one individual's user's view of the internet based on their email spool. So anyways, lots of fun stuff. Again, this doesn't really tell you too much about what's connected to what or what's going on. And the problem I run into with all these types of maps, all these types of representations, is you zoom in and you get nothing. You zoom into one of these big, topology graphs, like, great, what is that? And they can't tell you that easily. You can use some mapping software that can actually go to that level of detail these days. Most of the projects are really about creating fancy, pretty pictures, not about telling you something useful. So I was looking at one of my own personal mapping projects, and I was trying to find ways to make the data actually useful, and I'm also terrible at graphics. So it worked out well. So I mostly have tables and CSV files and not a lot of pretty pictures, but I'll do my best to hopefully come up with some cool things. So I want to find actually interesting stuff. I want to find, okay, is there a vulnerability in MySQL? If so, how many machines are actually affected by it? How is that changing over time? What about things like the VxWorks debug service that I was playing with? Is that actually getting better or worse over time? What particular regions are affected the most by this type of vulnerability? Those are all things I'm looking at and trying to find ways to get this data out of my massive project I've been playing with in the background. We'll get into that in a second. So it's one of those things where nothing I looked at currently really had the type of data I needed. So if you go all the way back to 1998, December of 1998, a group of folks, just random hackers, researchers, decided to audit the entire internet, as they saw it at the time. They looked at 36.4 million hosts, and they just scanned the crap out of them over 20 days for 18 specific vulnerabilities. What they found is over 730,000 instances confirmed exploitable of these vulnerabilities just in that population. It's about 2%. You also of services total. And 450,000 unique hosts, about 1%-ish, a little bit 1.3%, something like that. And you can see some of the basic stats here. It was a URL off the slide deck if you want to dig into it deeper. But the neat thing about this is the majority of their paper, of this presentation, this whole project, was so worried about what people would think if they saw this traffic coming in, and what would happen to them, and who would arrest them, and who owned different blocks, and how the military network wasn't more secure than this other network. And it's kind of a fun, fascinating, trip back in time to see how people thought of the internet back in those days. Was this nefarious area where everyone's watching you, and it's only, there's a centralized monitoring authority was kind of the background feel. These days, there's no centralized authority. We all monitor each other. Everyone's monitoring everything all the time. You're monitoring the monitors of the monitors these days. It's such an interconnected world that when you start actually doing large-scale network probes, you basically manage to piss off a large portion of the internet. And so I'll go into that later. It's a lot of fun. So fast forward a little bit, and you've got Shodan. I'm assuming most people here have seen Shodan. If not, it's a great project run by John. He does an awesome job of scanning the whole internet, putting it into one big Google interface, and letting you go through and analyze it to see what's out there. And this is the commercial pieces to export data to get certain types of queries, things like that. But it does an awesome job of making this stuff available for free for casual searches. Here you can see an example. If you search it for DerbyCon, it actually finds the one web page on the internet with a title of DerbyCon in it, and the IP to it, when it was last scanned, and all the information about it. So pretty neat that he just happens to run across just the DerbyCon page at this point. And that's a key point, because the thing is, the internet has gotten from this large, nebulous, scary thing that's hard to map to something that you can really do in just a short period of time with really reasonable resources. And that's why you can actually start doing things like this. Like, let's just scan the whole internet looking for my name. Like, why Google yourself when you can basically create your own Google and look for it? It's a lot of interesting things you can do to find information like this. Maybe going fast. We'll see how it goes. So he's got about 120 million hosts in the current Shodan database. If you look at the distribution of this, and especially back when I first started this project I was working on, it was almost all HTTP and HTTPS, which is where a lot of the World Wide Web is mostly HTTP. That's pretty standard. That's what people look for, what they care about. He's working on some research projects that really needed this data. So I'm not going to hold it against him that it was mostly this protocol at the time. But when I was looking at these ports, I realized that I need to find a lot more data. I want more SNMP data. I want more FTP data, more Telnet, more Secure Shell. A lot of the vulnerabilities I was looking at and trying to quantify required custom probes or a different type of probe than what Shodan was doing. So I had to, it'd be great to use Shodan for this stuff, but I can't use the data. It's not enough there. So I started looking into feasibility of doing it myself. Granted, since then, Shodan is now caught up in a lot of ways. They now cover almost the same ports I do, and we've been sharing code back and forth, so it's been a good project and a good person to work with. So I started looking at, well, I want to have data on at least these services. VNC, MySQL, POP3, SMTP, a bunch of UDP services, including NetBIOS, the VxWorks port, because it's always fun to mess with and see what's out there. Things like UPnP that previously were just not really well probed or assessed by anybody before. So now it's time to scan all the things. So scanning's awesome. So yay, packets. So some just quick math on sending lots of packets. There's 4 billion-ish IPs that are addressable on the internet. You really can't address most of them. They're multicast or segmented and so on. You only have about 3.2 to 3.5 really addressable target IPs on the internet. So pretty straightforward. If you have 4 gigs of RAM on a netbook, you can actually hold 256 states about every IP on the internet in that 4 gigs of RAM. So if you want to be really efficient about your memory use and tracking things, you could track the entire internet in one little 4 gig stick of RAM these days. Like resources have gotten to the point that they've actually caught up with our deployment, with our actual linear scalability of how we use computers. If you want to send a packet to every IP in the internet, it's really not that bad. It takes about 24 hours on one server if you're going to send everything. If you chop it down to just addressable IPs, you're down to about 17, 18 hours, and you can usually do this for about $7 or less. We'll go into more kind of what the costs look like for this stuff, but typically it's pretty cheap. So if you want to scan TCP services, use Nmap because Nmap's awesome, and then use it with a custom NSE script, and the URL to it's on here if you want to grab and look at it. It's crap. I can't write Lua with a damn, but it worked for this purpose. For the UDP side, I wrote a little quick C tool that just takes in a list of IP addresses, a data file, a packet rate, and a port number, and just spews it out. So one source port will cover the entire internet with one probe, or one entire class A's at a time. Like, it goes pretty damn fast. The nice thing about this is if you're trying to purchase a server, like a virtual private server, oftentimes you see these big honking Xeons or AMD servers running Zen or some other virtualization software, and they may limit your CPU resources and your memory resources, but they don't actually limit your network I/O throughput, your basic packet rates. So even though you're paying these guys $7 for an entire month of traffic, you're able to basically monopolize an entire like EE Pro 1000 card for that price. And I had this one Russian ISP keep telling me, "We think you're being DDoS." I'm like, no, that's cool. That's my traffic. I like it. Don't touch it. Like, do not block my DDoS traffic. This is awesome. Because they realized they saw my stream of traffic going out, but the amount of traffic coming back in they thought was a flood. But this was just replies to my probes. So, and that literally is $7 for an entire month. And basically scanned the internet 4 or 5 times before they figured it out and shut it off. So, well, there's some networks you don't want to scan from the US, and there's some networks you do. And this is one of the ones where all the IPs I normally wouldn't want to scan from the US, let's do it from Russia and see what happens. So let's watch it show up on CNN as another, state-sponsored attack. So anyways, fun stuff. So just that tiny little C application you can find in this URL, this can spew out about 1.2 gigs of traffic a day using 40-byte probes. So you can really hammer the crap out of a network card with it. I was running out of my 20 terabytes a month traffic limit on one server at the default rate, had to back it down to about 75,000 packets per second. So it's constantly sending out 75,000 packets per second, 24 hours a day for about 5.5 months now. And we'll share some of the data and packet counters and stuff. It's pretty cool. Works out really well. So unfortunately, scanning the internet annoys the entire internet. I've been the top attackers list of DShield for 5 months straight as the top 100 attackers. At one point, I was actually all top 5 of the top 100 attackers. All my servers got to the top of it. So I've been excluding people, and I've been shut off by one ISP, and having a lot of fun with this, but single hop and Linode have been great. The Linode guys went to the detail of organizing all my abuse complaints, finding out the IP ranges they complained about, putting them in a CSV file, and then saying, "Please, sir, will you block these?" I'm like, "Awesome, thank you, I love you guys." Then I realized that the bandwidth bill would have been like $9,000 to keep using them. So I was like, yeah, I love you, but not that much. So I'm going back to single hop using dedicated server for it. So I think my last queue, I've got like 1,200 open support tickets or abuse tickets at single hop. So those guys have been really nice. May or maybe not, because I found out where their support guys live in the Ukraine and sent them gift packages. So you also get some really fun responses here on the random crazy people on the internet that try to report you for scanning. They say, "This is illegal, you're hacking all the things." Like, I'm not hacking the things, it's a packet, get over it. It's the internet, welcome to the internet, buddy. So you have to see some really fun stuff here. Like, one state agency couldn't figure out what their IP ranges were and just drove me crazy because I was like, I want to block you, but you have to tell me what IPs you own. They're like, well, we don't know. Like, this is difficult. So how about you forward the alerts? Anyways, so it went around. So finally, this is all said and done. Like a week later, say, "We got a DDoS in 53. Any correlation?" Like, no, dude. Like, I'm not DDoSing you. Like, chill. Anyways, you get to find some really bizarre stuff. This one guy tried to report me to US CERT every week. So I just called, like, the US CERT guy was like, "Hey guys, yep, that's me scanning stuff. Enjoy. You want the data afterwards to go help fix the stuff? Great, okay." So it's been fun getting some of the replies back. So here's my mapping of dshield.org top 100. This is just a 6-day period, but the little red dot is my UDP scanner, and the rest of the servers in the cluster. And this is only the top 100. So I've basically covered the top 100 for 6 days straight with this little sample period. I've got data running for about 5 months now to track that, but I haven't had a chance to graph it yet. If you want to look at this from kind of a timescale perspective, the top clockwise, basically, so you go top, go around the right. Each one of the different colors pieces there is different servers' complaints. And this is the number of complaints by server over that 6-day period on 1-hour intervals all the way around. So you see these giant spikes of the big pink purple thing. That's all the different queued up complaints coming from single hop of all the people complaining about my UDP scans. Then you see these big green spikes. Those are all the web crawlers, the SH scanners, things like that coming in. And they see they slowly kind of spiral down as they start adding different people to the exclusion list. So it's been fun to watch kind of how the data has changed over time as well. As far as the amount of data itself, it generates about 5 gigs of data per day, compressed. About 700 gigs of data so far, and if you actually normalize it and crunch it down as small as you possibly can, and then sort it by timestamp, and spend a week and a half sorting all this crap in a box with like 200 gigs of RAM, you get 330 gigs so far. So it's a lot of data to archive off still. And it's all being stored in Mongo and Elasticsearch. Mongo has both a state table of the most recent banner per system, as well as the entire historical view that's being loaded now, but it's 6 days into the load process, like 3 or 4 to finish. Elastic is a nice search engine if you haven't used it. It's based on Lucene, but it lets you quickly search any kind of document you store in it. So that's all kind of the setup, the reasoning, kind of the mindset, why I started doing all the stuff. And then I want to jump a little bit into the results a little bit before we go into the really crazy stuff. If you look at the breakdown of all the services found so far to date, you can see, port 80, the far left on your side, is definitely most common at 91 million hosts. Next to that, you actually have UPnP. So the SSDP service on port 19 of UDP is more popular than any other service within HTTP internet-wide, which is a very unexpected result looking into this, because who the hell has used SSDP and port 1900 externally on their firewall before? So there's something like 53 million devices that have this exposed externally, more than any other service other than HTTP in the world. And the next one down, there's actually SNMP. So who would have thought SNMP is this widely exposed as well? That's around 43 million hosts. And I just kind of cycle down, you start seeing less and less and less and so on. But it was kind of fascinating seeing how these, what the relative values were for these different services. So it currently covers about 227 million unique IPs, and of that, it's about 550 million unique service banners, about 1 billion records total overall. So I scanned every single IP in the internet, 0/0, for every UDP service every 7 hours, 5 months. So if you have a server, I've scanned it, I'm sorry. It's for the TCP, you can't really scan that quickly unless you're Dan Kaminsky. He'll probably talk about how you can scan better than I can after my talk, which is great. But I ended up using Nmap and doing some spot sampling. So basically telling Nmap to run with 250,000 random IPs at a time, and then running 8 of those per server, and then 6 servers, and then each one of those is sending at 50,000 packets per second. So and that's just crunching along in the background, scanning random blocks of IPs all the time. And I'm doing that to avoid port scan filters, things like that, but only doing one port here, one port here, one port here, all from IP ranges. So it's been taking a while to do. But what's interesting is that if you combine all the web services, HTTP, HTTPS, port 8080, that ends up making 145 million entries. And that's interesting for stuff later on. The one server that I've got at single hop doing all the UDP scanning hasn't been rebooted since I started the project. So I've actually sent 570 billion packets and transmitted 57.8 terabytes of traffic. And these are 40-byte packets. It's just crazy amounts of data. So it's kind of fun stats about what happens when we actually start running this stuff for a long period of time. On SNP, we mentioned this 43 million, but SNP is a pretty scary freaking protocol that I've exposed to the world. SNP will tell you all the different routes, all the IPs around that IP, all the neighbors basically in the ARP cache, any running processes and services in Linux and Windows, and you can install software patches on the same versions. Account and group names, you can actually enumerate user accounts to SNP on Windows as well. And of course, you can DDoS the crap out of everything with amplification attacks by requesting something that has a very large response, sending a small query to it, spoofing it. You can swing like 150 terabit DDoS pretty easily with just a small portion of these with 100 megabit link. UPnP was something that surprised me because I hadn't really seen it pop up before. Like, yeah, there's some like SOAP attacks and port mappings, things like that, but it wasn't really something that was widely recognized as being a risk, and it still isn't right now. The reason that I feel like it is a risk is there's only about a dozen unique implementations of the UPnP software in the world being used. Because the banner will come back and tell you what SDK is being used. And they're almost all based on Intel SDK for UPnP devices. That was written in 2001. It looks like it's all stringcat, SPRNF. I mean, it's every nasty bug you've ever seen before. There's format string bugs and a lot of it. And all the different vendors just basically took this reference implementation, forked it, and used that to ship like the Netgear version, the D-Link version, and so on. It may not be those direct vendors, but there's some vendors who just directly forked the Intel SDK. So you've got this massively potentially exploitable vulnerability and a protocol no one's really looked at that exposes more devices than anything else on the internet other than HTTP, and no one knows about it. So have fun. There's lots and lots of bugs there. I've been looking into a few of them. I just haven't had time to really dive into it yet. And the next thing we talk about is kind of density. So you start looking at overall the IPs on the internet. How do the services line up? How do they line up relative to each other as well? So this is what I was up to 4 in the morning making little pretty pictures for. And what this graph is, internet spark line, as I call it. On the far left side, you got 0.0.00, and the far right side, you got 255, 255, 255, 255. And that big empty block in the bottom, and the far right side, those are all your reserved multicast, et cetera, that don't respond. If you're looking for Google's DNS server, it's pointed out right there at 8.8.8. If you're looking for where you are today, if you're connecting from this hotel's Wi-Fi, it points to like 70 something or other. That's where the IP range I got for it earlier. You see these nice big spikes, and then this kind of the amplitude of the wave basically is of the signal there. That's how dense the particular measurement is. So if I'm searching for port 80, it's how many port 80 devices there are across an entire IP range. So you can look at this as kind of like a trend line for the entire internet for a particular service, port, or measurement. Hopefully this makes some sense. It's just random visualization I tried to come up with to describe this stuff. It's really tough to crunch that many records in a way that's visually consumable. So we'll see how this goes. The first comparison we'll look at is web versus FTP versus telnet and SSH. So you see some fairly regular patterns as you kind of go down. So the same IP address at any point in this graph, as you slice down, will cover port 80 on the top, SSL, the next one down, 8080 below that, FTP, telnet, secure shell. So if you want to see how many web servers on average have both, how many servers have port 80 open as well as port SSH open, you kind of look at the top line and the bottom line and kind of run the two together and kind of do a visual slice down. And you can see that for certain subnets, they correlate directly. For a lot of subnets, they don't. Right down the middle of this, for example, I'm not sure if you can see the mouse on this thing or not, probably not. But if you look kind of 30% into the graph on the left, you'll see this big spike web servers here and then SSL servers and then almost no secure shell for it. So you've got a massive cluster of web servers that aren't being managed through secure shell. Then again, you've got some other spikes where they are. So it's interesting to see how the telnet and all these other protocols line up. Now for me, the scary thing is FTP and telnet don't really do encryption. Yet they're actually much more popular than a secure shell by far. And looking at secure shell versus telnet, sorry, let me pull back. Looking at secure shell versus telnet, you see that telnet's still more popular than secure shell by far. And FTP the same thing. So if you look at how far have we come in the last 30 years or 25 years of doing internet security, not really if you look at it from a macro scale. We're still using unencrypted management protocols for the most part. This is a separate graph where you still have your HTTP, HTTPS, 8080, your web protocols in the top 3 bars. And then the next lines down, you've got SNMP, UPnP, and NetBIOS. Now the fascinating thing about this, if you look at the SNMP line and the UPnP line, they almost directly correlate. These are really crappy modems and devices, ADSL modems, little VoIP phones, little devices that are just poorly secured, that are embedded devices that are sitting on the internet and are exposed at least through both SNMP and UPnP. So you're looking for, what's the biggest exposure we have on the internet right now? It's SNMP and UPnP. And you can see they almost line up directly. Almost anything with SNMP open is going to have UPnP open as well on average for any particular /16. Each individual line on this is a class B. That's the smallest granularity, and they're calculated by port, so just gigantic MapReduce job to get it all out. And then you see NetBIOS at the bottom, which is kind of fun. You see it's actually a lot less popular than either one, but still spikes up, still some different areas here. And one thing you'll notice is any place where you've got a NetBIOS service popping up like this, you've got exposed Windows desktops to the world. So those are your exposed Windows desktops to the world. By the way, this doesn't include devices that are Samba. I took all the Samba ones out of this graph. This is just ones with real MAC addresses that are Windows. Samba always returns a 000 MAC. So, anyways, so the next graph here is a little bit different. But what I did is I asked the generous folks at Zone H to give me a copy of the last 3 months of defacements. So all the websites that were defaced in the last 3 months, and I took all the 42,000 unique IPs of 256,000 defacements, was a lot of vhost defacements, and then amplify that graph by 100 so you can actually see it line up well. Amplitude, the vertical is amplified, but the horizontal isn't. So as you kind of do slices down, you start seeing where the defacements line up with what services were exposed on a macro scale. So one thing you'll notice is FTP and Secure Shell generally line up pretty well, some of the big spikes in defacements. You'll see HTTP, of course, does, because it wouldn't be defaced unless it had a web server on it. So that's pretty accurate. But it's kind of fun seeing how all this stuff lines up. I'm not sure there's any real value in this particular representation, but it's fun to look at and kind of see how different things correlate. Next thing I want to look at is email services. This is hilarious because I spent so much time scanning not just 25 SNTP, but also 143, 110, 993, 995. And I was like, great, I've got all this awesome data about IMAP and POP3 deployments. And then I did this graph, I'm like, what the hell, man, I was wasting my time. Like, SNTP almost guarantees that you've got one of these other ports open. If you can find any device with 25 open, it's almost going to have POP3 IMAP, POP3S, and IMAP-S open on average, just by looking at the data set. So this is kind of scary. It's like, wow, you don't just have SNTP open. If you had a mail server, it's a mail server, and it's exposing mail lots of different ways. So on average, mail servers are not just places you deliver mail to, they're actually where people are checking their email from as well. So it's a fun kind of correlation on this, and it made me sad that I spent probably way too much packets scanning ports I didn't need to. This is the breakdown of UDP services. So you've got SNMP, UPnP again. You can see how closely they correlate. You've got NetBIOS again, which shows how it kind of lines up with exposed public Windows systems. But then you have MDNS, and MDNS, also known as Bonjour or Vahidi, it's the service that does auto service discovery on OS X, and it's now been ported to lots of other platforms. I had to do a 10x zoom so you can see it at all here, because it's much smaller than the rest. But you kind of see how this correlates with other exposed devices on the internet. Generally, MDNS is only exposed on certain NAT gateways. TiVos, for example, expose MDNS. Most Mac desktops plugged into the internet expose this to the world. Even if you have the firewall enabled, they still expose MDNS. That's how they work. And then the second level down there is VxWorks. These are devices that have this vulnerability that allows you to manipulate remote memory of any of these embedded devices in a very precise way through a remote debugger, basically. And you can kind of see how these things correlate. So what the funny thing about this is if you look at the way that SNMP, UPnP correlate with VxWorks, it still points to a bunch of really crappy embedded devices on the internet with no security. And they do line up pretty well. You do see some spikes here that don't have SNMP but are VxWorks and vice versa, but it's kind of fun to see all this stuff lined up. So this could just be like, visual wanking for all I know, but I thought the stuff was fun. And finally, last one I'll show you is some less common services. If you want to look at how often MySQL is exposed to the internet, or VNC is exposed to the internet, relative to SNTP or Secure Shell, it just gives you kind of a general weighting for it. So you see VNC is not really that exposed, MySQL is not really that exposed, but they're both about the same level of exposure. People actually stick their databases on the internet to the same level they expose their desktops to the internet through VNC. And actually, it's not that far off from Secure Shell. So that's funny Sparkline stuff. I figured we should go into some of the more interesting findings at this point before I run out of time. Stuff I want to delve into next is how do you actually measure vulnerability? So if I've got a particular way to break into servers and I want to find out where those servers are on the internet, how widely they're exposed, how that changes over time, how can I go get there from this data? The first example I want to talk about is VxWorks again. This is a fun little remote debugger service. You can use it to do like save game hacking style modifications to embedded devices where you do a memory dump of the device, you make a configuration change of a device, you figure out what changes in memory after you make that change, and then you poke that memory back in to force that change on someone else's device. So for example, you can use this to enable auto answer on video conferencing systems and enable them to automatically pick up the H323 line, and then even if they previously had a password set, you can overwrite the password in memory, set the auto answer flag in memory through a remote debugger poke, and then just dial into it and monitor the room and listen to audio. So there's some really neat kind of useful things you can do with this. The fun thing about this stuff is actually the same hardware and software is being used on things like the Mars rovers. I've got a fun visit soon to go see some of the rover folks and talk about it. And back in July 2010, I found about 250,000 of these devices exposed to the internet at the time. So we went on this huge campaign with US CERT kind of running with it, talking about, let's contact all 112 affected vendors we identified, get them all to fix their stuff, put patches out there. We spent all this time getting up and running. We're like, yay, internet hero, and we just failed. Didn't make a damn bit of a difference. 2 years later, the devices that are still running and haven't caught on fire because it's all crappy electronics, there's still 200,000 of these things sitting out there. So disclosure might be great and make everyone have a warm fuzzy, but it doesn't really make a lick of difference on the internet. Next thing we want to talk about is MySQL. MySQL is awesome because if it doesn't like your password, you just keep on trying. The joke is you've got about 3 million servers on the internet expose MySQL. About 1.5 million don't even have host ACLs, which means you can just brute force them all day long. And if you have the right password or they have a default password, you just log right in. And they're all vulnerable to known flaws. Authentication bypass flaw is fun. The authentication bypass flaw, basically, it requires very specific versions of MySQL, very specific architectures and package names. So it's really tricky to figure out exactly what's vulnerable without doing a lot of other fingerprinting and testing on this stuff. About 2 months after the bug eventually came out, I started digging into it and found out there's about 90,000 of these MySQL servers exposed to the internet still. So you want to talk about data loss. You just keep trying to log in until you dump the database. You can actually automate the entire thing from a shell script in one line to go automatically hit random machines on the internet, dump all the data to a file, and then send it off to, whoever you want to. So it's just ridiculous how bad some of these vulnerabilities are and how exposed the internet is as a whole. Another example I'm looking at is the F5 Big IP SSH exposure. This is a really fun advisory where F5 mistakenly shipped the private key to their device on the system that accepts it. So every customer has the private and public key to their system and then everyone else's systems. So you have the Secure Shell private key, you can then log in as root to any one of these F5 machines that had this particular vulnerability. So it's about as hard as it gets for hacking. You just do sh-i root at host, and you have a root shell. So it's pretty straightforward. So this was published in June 6th. The public key was actually published as well. So the nice thing about the public key and secure shell authentication is if you have someone's public secure shell key, you don't really need the private key to tell you whether that server will accept your authentication or not. You can actually do the authentication process, like go all the way up to the point that says, yes, I've got this public key, will you accept it? The server says, yes, I will accept your public key. And you say, thanks buddy, bye. So instead of actually, you can pretend to have the private key basically and use that to figure out whether the server will accept your public key without actually logging into it. So I turned this into a vulnerability scanner. It's baked into Metasploit for doing this kind of half SSH scanning. So it uses identified pub keys module with the public key exposed by this advisory, and it starts scanning all the machines I found in my giant database that matched F5 fingerprint for the web UI. And it found about 721 machines still exposed accepting remote root login as of August 15th. And this was published June 6th. So again, no one really cares. 10% of the population exposed to the internet are still vulnerable 2 months later, even after F5 started calling all their customers trying to get them to fix this stuff early on. And I've actually provided a list of IPs to the F5 back in mid-June, early July to help them kind of solve these things. So as you can see, people don't care about security, and we're all rooted and we're all screwed. That's really it. So next thing I want to dive into is Cisco routers. Cisco routers are fun because they're a pain in the ass to figure out, it's just secure for the most part. Because people just ignore them until they break. They treat them like doorstops. Cisco puts out about 40 advisories per year for iOS, and most people don't flash their routers more than once every 5 years, as the data currently shows. Does anyone here actually flash their routers regularly? It's lonely out there. Well, the downside is if you load the wrong image, the router crashes, the pain in the ass, the protocol suck. These aren't devices meant to be updated. They just do a really poor job of managing update process. If you look at all the different routers out there, you query them. So in this case, I took the SNMP data. So I looked at the SNMP version information from about 360,000 Cisco iOS routers that are exposed to SNMP public, and then crunched what particular flaws they'd open. And the average router had about 60 flaws exposed based on configuration, version, and so on. The most exploitable version on the planet is iOS 12.2. It's when they added a whole slew of features that all have vulnerabilities at once, and no one ever upgraded past them. So if you're trying to exploit a Cisco iOS bug, the tricky thing is you need to know all the little magic numbers. You have to know what architecture it is, what platform, what type of CPU it's got in it, NDNS, the image itself, lots of little funny stuff you need to be able to precisely target your exploits in these things. So if you want to do, first thing it is break down all the devices I found based on hardware type. And as you see 7200s on the far left, the most popular. The keys are the very bottom lines. 2800s the next, 1841, C870s, and so on. So if you're looking for, if I wanted to exploit a whole bunch of routers and I want to target more than 20,000 of them, I'd go after a 7200 right now. So if you look at the 7200s, 2800s, 1841s, or C870s, and you try to find exactly what version has the most flaws based on that hardware set, and you basically optimize your targets, you see that you've got about 12,842 routers on the internet are running 12.4, 15 train 7, which has the largest number of vulnerabilities for the most commonly found hardware platform. So it's kind of min-maxing Cisco router vulnerabilities to figure out what the best target you have to create an internet worm around Cisco iOS is, if you're a bad guy. So I was like, wow, this is awesome. Like this 12,000 routers would be the most vulnerable population for a new exploit targeting Cisco iOS, or even an old exploit targeting Cisco iOS. And then I decided to say, well, let's just scan all of those routers again, but this time let's use private, not public. So 268,000, sorry, I misspoke earlier, Cisco iOS devices had public open. Anyone want to venture a guess how many actually had private? Okay, a couple of guesses. It's actually 18,000. So 18,000 routers on the internet, you can rewrite the running configuration, dump their password hashes, reconfigure them any way you want without doing anything other than one command line in Linux. So it's kind of pointless to write Cisco iOS exploits, because you can just use SNMP to do it all for you. So this is sad. I was like, oh, I could have been a hacker and done lead stuff, but I can just use SNMP. Never mind, okay. And this gives you full access to everything, right? So I'm going a little short on time, so let me try to hurry up a bit. SNMP and Windows does all sorts of terrible things as well. It lets you expose, like we said, Windows account names, account password hashes in some cases through the service arguments. If you look at the listing of 332,000 machines running Windows with SNMP exposed to the internet, the really weird split on this graph is that the far left side is 2003 and XP at 184,943. Next to that is Windows 2000, with 140,000 Windows 2000 boxes still out there with SNMP exposed to the world. Next to that, you got 2008 and Windows 7 with only about 3,400. And then you've got Vista with 1,285, followed by Windows NT 4.0 with 1,281. You actually have almost more NT 4.0 boxes on the internet than you do Windows Vista. That's how unpopular it was. And finally, the last point of this graph is NT351. There are 7 of these bad boys out there just trucking along. They're probably still using like trumpet windsock for all we know, and they're just kicking it. So we got to figure out what hardware these things are running on and clone them. These things are amazing. So we start looking through, what I did is I took all the Windows machines out there, and then an SNP walked all of them in this big cluster, and then dumped all the data and started going through it. If you look at the common process names, obviously you see things like service hosts, all the different common Windows processes that should show up here. But let's say you flip that on its head and say, let's find the least common process names running on these machines. We've got some really weird stuff like 90.txt is a running process name. That's totally legit. You find some really just odd stuff out there. And so the tail end of this, kind of the long tail, ended up being something like 12,000 processes I couldn't identify that didn't match any known signature running on these random boxes. So these are all just malware infested, who knows what. So you start looking at the really fun stuff out of here, and you find these really weird name processes, like blackcipher.aes is a process name. It's like, yeah, that sounds good. Or adobeupdate.com was a very common running process name. So there's a lot of idiots out there running Windows 2000 clicking things. I don't even know how they do that, but so some fun stuff. I know I'm getting a little short on time, so I'll skip along here. One thing that's neat about SNP is you can enumerate all the running services and the arguments to those services, but oftentimes those arguments contain passwords to other devices and systems. So in this case, you've got about 1,000 clear text passwords just sitting out there. And these passwords are to cooler things in Windows. They're to things like secure shell servers, databases, retail applications to go in and manage all your funds and all your purchases for a particular day, all kinds of cool stuff. So you find RDP passwords here to other servers, and it just gives you an idea of just how screwed we all are looking at this stuff. But it's just amazing that like something as easy as SNP that a lot of vendors will enable on an otherwise totally locked down, patched, decent system will then expose your clear text password to another server because of how a particular service was configured, and no one ever took that into account. So going on to NetBIOS. NetBIOS is great, and by NetBIOS I mean 137 UDP, not this fancy SMB stuff, just basic UDP probes. So if you query a machine with NetBIOS, it'll tell you its MAC address, it'll tell you its name, group name, and previously the username. You can actually then query it again and say, okay, tell me all the IP addresses for this host name, and it'll tell you all of its IPs as well. So you can actually find multi-home machines very easily through NetBIOS. It's a neat trick for doing pivoting on pen tests. And you'll find that module baked into Metasploit already, and it already does it. It works great. So if you look for machines exposed to the internet with the NetBIOS, basically no firewall at all, just hanging out there, about 21 million devices. But you look at MAC addresses, and most people look at MAC addresses as something that's a unique fingerprint of your device. You always worry when you're like, we're driving, someone's going to fingerprint your MAC address, and someone's going to come call the feds on you. They're going to say, oh, yeah, I found your MAC here, here, and here. Or a lot of college campuses do port locks based on MAC, or they do a lot of just tracking based on MAC addresses and DHCP pools. So generally, MACs are considered this like identifiable thing, right? Except for they're totally bullshit. People, not just people obviously change their MAC addresses all the time, but it's not a very common thing. Your grandma's not going to change her MAC address. She just doesn't really care. She's not hacking somebody's Wi-Fi, hopefully. What you will see is a lot of vendors will reallocate the same MAC addresses extensively to the same population. Huawei is the worst offender with almost 300,000 MAC addresses that are duplicates across their population of deployed devices. Qualcomm is pretty bad as well, something like 65,000. Asus, of course, and the one that doesn't strike me as weird is VMware, because VMware is going to give you, they're automatically generated addresses based on, fingerprint of your system, things like that. So VMware should have conflicts, but HP shouldn't, Dell shouldn't, Hyundai shouldn't, Microsoft shouldn't, Intel shouldn't. These are all based on the OUI list. So if you ever thought a MAC address was unique, this should change your mind, because I can give you the raw data for it. Most MAC addresses are not unique, actually. There are 2 addresses that are actually widely used that weren't represented in that previous data set. They don't map to any known vendor. And if you ever find a machine with MAC address 53, 45, and all zeros, that's Windows XP. If you find one with 44, 45, 53, 54, 42, that's Windows 98. These are the dial-up networking adapter MAC addresses. So if you have a PPP link or a dial-up link, this is the MAC address that will come back with when you scan it. So you can easily go through and scan. This is a quick query on Shodan for this particular MAC address. And this shows 32,000 Windows XP systems dialed up to the internet on dial-up. Still blows my mind. And this one's called FBI-something, what seems neat, in Moscow. So it's some weird stuff out there. If you look at the names themselves too, the names will actually tell you a lot about the system. They'll tell you, if you search for a unique name like CALEA is a really cool term. Who knows what CALEA is? All right, so CALEA, C-A-L-E-A, it's the law enforcement regulation for how ISPs have to give access to law enforcement to tap their networks when their users are under observation. So if you just search for CALEA in the MAC address or in the NetBIOS name, you find a whole bunch of stuff. You find all Frontier Networks CALEA systems. sitting on the internet with no firewall. So going on, a lot of times you'll find different pirated versions of Windows use a very either hard-coded MAC address or a hard-coded system name. If you search for Dark Edition, you find all these hacked versions of Windows XP that have like a black theme, this and that. They're all hardcore and hacker and so on, but they don't get Windows updates. So they're the most vulnerable XP machines you'll ever find on the internet. You can find them all in one swipe by searching for the NetBIOS name. Or if you're trying to find a particular company, I just picked a random company up, said AXA Advisors, you find all of their machines. Anytime these machines pop up onto a Wi-Fi network or a Starbucks coffee shop that has an external subnet, you'll see these things pop up right away. So you can actually track people over time. I've actually found one of my company's resellers in the UK, I keep finding his laptop on random networks in the UK, and actually in the rest of Europe as well. I'm like, hey, you popped up in Belgium. Hey, you popped over here. He's like, what are you doing? Like, turn on your firewall, dude. What's wrong with you? Like, I think you're outside my purview because he's a reseller, but still, it's like, come on, man. I'm like, try harder. He's got a unique name, so it's easy to find. And I confirmed that it was him and so on. So last thing I want to talk about, or almost second, yeah, about last thing to talk about, then we'll do questions real quick, is HTTP cookie analysis. So if you look at every web server on the internet and you take a look at the cookie that it provides you and you try to browse to it, these are typically session cookies. They're supposed to uniquely identify you as a user to that web server, and it's supposed to be unique and magical, and no one will ever know your secret number. That's how cookies are supposed to work for session authentication. What if they weren't? What if they actually weren't unique? If you look at 145 million web servers and start crunching those cookie values and saying, hey, which ones actually collide, you find some really wacky stuff. So in this case, it's a little bit tough to see on the screen here, but these are 5 different cookie values that conflicted, and it's ASP, classic ASP cookies. These are like Windows servers that have IIS like 5.0 or 6, are giving out the same ASP session cookie across almost 300 servers in one case, 133 servers in another case, and 25 and 25. And you wouldn't have found this unless you actually look at all 143 million and start crunching them to figure out that there's conflicts. But why in the world would the almost 300 IIS web servers giving out the same cookie to multiple scanners across the internet? I'm not sure about you there. Oh, I had another slide on there. But essentially, these are all random fake IIS servers run by the Chinese government. And these are scattered across multiple ISPs all across China. And they're all front ends for something, but they happen to give, they try to pretend to be these IIS servers, and they give you this single fake cookie, and you can easily identify them based on the fact that the cookies are not unique on the global scale. That's really weird. So you find some stuff that pops out there like, oh wow, yeah, these are all Chinese government boxes. Hey, they've got some weird admin interface I can't log into, and they try to pretend to be IIS, they're not really IIS. It's pretty odd though. If you start looking at other cookies, especially ones with very unique names, the Twisted framework, for example, in Python for doing network services, actually had a fairly high level of collisions. At the high end, you see 4 or 5 machines have the same Twisted session ID. Why would that ever happen unless there's something really broken with Twisted Sessions PRNG? So if you know anyone who maintains Twisted, ask them why the hell all the cookies are the same. At least the same enough that over 143 million servers are enough conflicts here to pop out. You also see some Ruby on Rails stuff. You see some rack session IDs being either unique across 58 different servers. You see federal_session being unique across 54 servers. So it's pretty interesting what kind of random web application framework 0-day you can find just by looking for conflicting cookie IDs. Taking that one step further, I'll make sure we have a little time for questions here. If you look at embedded devices, they actually have similar problems. A number of cable and ADSL modems. If you look across all 143 million servers, and these represent about 30 or 40,000 devices, you'll see that some of these RG cookie session ID values are actually duplicates across 10 servers, 9 servers, 8 servers. This gives you an idea that once you find one of these things, that these things you can probably brute force a session on your own. You just keep throwing IDs at it, you're eventually going to hit it. It's probably going to follow some very repeatable pattern. So you know that there's something definitely wrong with these systems in terms of how they generate IDs, and this leads you to, okay, what's the next avenue attack? Are these machines being compromised next? Somewhat surprising was ACE, the Cisco content caching application control engine stuff by Cisco. Seems to have a similar problem. If you look at ACE cookies, you see 130 machines have the exact same ACE cookie value. You see there could be a really widely deployed cluster because they weren't sequential IPs, and they're scattered around, so it looked odd, or there actually is a conflict in their session ID generation. Anyway, so lots of weird stuff. I'm still digging into the data. I'm going to keep running this project for probably another 6 months or so. If you need access to any particular raw data for your network, for a particular application, or you're working on a research project, drop me a line. My contact info is pretty easy, HDM at Rapid7 or at HdMoore or HDM at Freenode. And again, thanks for your time, and we'll go to questions. Fortunately, I can't see anybody to ask questions. So, okay. So, first question in the front row. The question was, in the duplicate MAC list, the gentleman didn't see Hyper-V or Zen or other virtualization solutions. That's correct. I only showed the top 10. Those actually show up further down. There's more conflicts for VMware. So it's actually a good test of how popular VMware is relative to Zen. What's the question far back there? Okay, gotcha. If you want to holler it out, I'll repeat it. Yeah, the question was the experiment being run over a couple months? Correct, it's been running since May. Question was, what kind of variance am I seeing on how the metrics are changing over time? When new vulnerabilities come out, it's kind of fun to watch a very small subset of the population patch immediately, and then the rest of them kind of tail off over about a month or two. And then you see a small section of the populace never patch at all. So for the vulnerability, I've really been looking at the vulnerability side for the trending piece so far. I haven't looked at like general service exposures yet. Nice. But if you want to take a look at the data and take a shot at it, go for it. No, it'd be kind of neat to see. Sorry, yes, sir. There's a question in the back with a green shirt. Or black and green. Sorry. The question was, what are the differences between port 80 and port 8080 in terms of what services were available and what stuff was exposed? It's a really good question. 8080 found a lot of application framework admin interfaces, device admin interfaces, stuff that just didn't show up anywhere else. Originally, when I was looking at the showdown data, they didn't cover 8080, and it missed a lot of the queries I was finding on 8080 later on. I'm trying to remember the name of the application offhand, but a lot of proxy gateways, a lot of admin systems for embedded devices, and a lot of NAS admin services were all exposed to 8080, but nowhere else. What's the question? The green shirt in the third row back up here. Sorry.
Yeah, I was just wondering if you had researched TCP v6 at all.
I've looked into v6. The tough thing with v6 is you can't just sequentially scan. You have to do some other fancy tricks to find IPs. So I've got all the scanning tools supported. I just haven't had a chance to go tackle it yet. What I've been doing instead is enable most of my sites to enable v6. So I'm collecting IP ranges where I know clients are, and then I'll go after them later. So don't browse my website with v6, you end up in the list. So, there's a question from front, yes, sir? So the question was, are there particular net blocks that were more or less vulnerable than others based on organization name? Unfortunately, I didn't get a chance to finish my errand mapping yet to do organization versus net block, but what you will see is anything on this list that I'm about to pull up, the spark lines for SNMP or VxWorks, indicate vulnerability. So in this case, the top line there, those are net blocks versus exposed SNMP devices to the public, and there are very clear trends of what net blocks have what vulnerabilities there. If you start on the left, kind of move your way over, you see like a lot of like 65 to 72 Class A range, basically. Helps. Jason, the white shirt? The question was the Cisco trains 12.2 and 12.4 were very popular for GNS3 or Dynamips emulator. Were those potentially dynamic routers or virtual routers? Based on where they were, it doesn't look like they were. Just there wasn't like a concentration of them. It was just fairly one-off. They look like they're supposed to be where they're supposed to be on the network. I apologize if I didn't get to your question. I think we're getting to the end of time. And I'm happy to take questions during one of the breaks going forward, but we should make room for Dan Kaminsky. Thank you.